Hello and welcome. So I'm currently learning R and thereby found a pretty interesting implementation of a logistic regression predicting whether the stock market is going up or down on the next day. The code in the book where I found this is written in R, so I thought it would be interesting if we were doing a Python transformation and thereby improve our skills in data handling and machine learning. Before we are starting, some important remarks. So this video is based on the textbook Introduction to Statistical Learning with R, and you will find the example in chapter 461. And the book is freely available online. I'm just transforming the R code into Python code, but R knowledge is not required from your side, so you won't see R code in this video, just the Python implementation. The book content is not shown, but I'm referring to it, so it is recommended to check out the book besides. Finally, if you want to provide feedback, the presented model is not my idea. I might not be the right addressee for conceptual criticism, but of course feel free to do so anyways. Even more important than that, if you like this kind of content, please like this video and subscribe to the channel. Only 10% of my viewers are subscribed, so please change that. Thank you very much in advance. So, logistic regression in a nutshell, just one or two sentences. A logistic regression is a machine learning algorithm for classification problems, and it is predicting a binary output. For example, is a mail spam or no spam? Or in our case, is the stock market going up or down the next day? So please read yourself in. This video is not containing conceptual explanations, but if you need any support, please feel free to drop me a comment. What you are seeing here is a data frame in R. This data frame is part of the ISLR library. Again, you don't need to understand how to get this in R, but you need to understand what this data frame is containing, as we want to replicate it in Python where we don't have this ISLR library. So this data frame contains the daily returns of the S&P 500 from 2001 until 2005. The today column is containing the relative price change of the day, and the direction column is containing the value up if this value is positive and down if this value is negative. The lags are just the prior n day returns. So lag 1 is the return on the prior day, lag 2 the return on the day before the prior day, and so on. The volume column is containing the volume of the prior day in billions. So let's build that data frame in Python. Okay, so let's get started with importing some necessary libraries. We need pandas for data handling, we need yfinance to get the S&P 500 returns, and for the logistic regression we're using the statsmodels API. But as an alternative you can also use the sklearn library. In the next step we are getting price data for the S&P 500, and I'm storing that in a variable which I'm calling data. Use yf.download. Provide the ticker symbol for the S&P 500, and I'm starting at the beginning of 2001 and I'm going until the end of 2005. So let's see what we got here. So we are getting this data frame here, and to get the daily returns I'm just using the PCT function over this column, over the adjusted close price. So I'm creating a new variable here, which I'm just calling df for data frame, and take the adjusted close column now and use the PCT change function. What I'm also doing is multiplying that by 100 as the authors were taking the values in percentage. So we are just multiplying that by 100. So let's see what we got. As you see, we're getting this series containing the S&P 500 returns. And let's just rename this. So we are just using df.rename, and let's just call that as it was in the data frame in R. So this was the today column. And now we are resetting the index of that to create a data frame out of this series. So I'm just using df underscore reset underscore index. So as you see, we're getting a data frame here. And now for getting the lags, I'm just using a simple for loop, and a lag is working like that. So let's take this date here as an example. So the prior day return of this day is just this value here, right? So I can just shift the values by the lag. So the lag 1 value for this date would be this value. So I can just simply use a for loop and just create 5 additional columns here and shift the values by the particular lag. So how can we do that? We are just using for I in range, and we are looping from 1 to 6 because 6 is excluded. So we have 1, 2, 3, 4, 5. And now we are just using df and provide lag plus, and now I'm using typecasting and take the iterator here. So in the very first iteration, I would just get a column named lag 1 here. Second iteration, lag 2, and so on. Okay. And what I'm doing now is I'm just taking the today column here. And as I said, I'm just shifting and then take the iterator here. So for the first iteration, I'm shifting 1 row, for the second 2 rows, and so on, right? So let's see what we got. Now we see we have those additional columns here containing the lag returns. And again, you see here, so on this value, as I just explained, we are just getting this value here for the lag 1, right? And on this day, for lag 2, we are getting this value here. Makes sense, right? In case it doesn't, always drop me a comment. What we also need is to get the volume of the prior day, if you remember the R data frame. So I'm using the volume. So I'm creating a column, which I'm calling volume here. And now I'm using the data frame, access the volume column, and just shift by 1 day. So to get the prior day volume. Take the values out of that. And what I'm also doing is I'm just dividing that value by 1 billion as the authors were using that scale. Okay, so we have to do that as well to make our results comparable with their results. Okay, we've done that. And now what we are doing is we are getting rid of all those NaN values and every row which is containing a NaN value. So we can do that easily by just assigning df.dropNA. And now we are getting the exact same data frame as we just saw in R, right? Well, one thing is missing, and that is the direction column, right? And as explained, the direction column is up when this value here is positive and is down when this value here is negative, as you remember. Now I'm slightly deviating from the authors as I have to because of the statsmodels API. So if you are using sklearn, you can use up and down, but I have to use 1 and 0 instead of up and down. So 1 is for up and 0 is for down. So I'm creating a new column here, which I'm calling direction, and I'm just specifying 1 if I is larger than 0, else 0 for I in, and then I'm just taking the today column here. So what am I doing here with this syntax? I'm just checking in this column if every single value is larger than 0, I'm getting a 1, and if this value is smaller than 0, I'm getting a 0 here. Okay? Or in sklearn, you would use up if I is larger than 0, else down for I in df today. Okay? That's fine here. So now we are getting the exact same data frame as we just saw in R. Now, what we need to do, because of, again, the statsmodels API, we need to add a constant to our data frame. So in statsmodels, if you're not adding a constant, your regression is not containing an intercept. So we have to do that. And we can just use sm.add_constant, then provide the data frame. And what I'm doing with that is I'm just adding a column here, which is just containing ones, okay? So now I have a constant. Okay, now we have everything what we need to perform a logistic regression. So yeah, what we are doing now is we have to define the independent variables and the dependent variable of this regression. And just as a quick explanation, if you are not following along with the book, what the authors want to do is they want to use the lags and the volume to predict the direction. Okay, so in this logistic regression, the independent variables are the lags and the volume, and the dependent variable is the direction. Okay, so we are defining x as the independent variables, and we're just using df. Now provide the constant column, then all the lag columns. Wow, this is really inefficient, sorry for that. So lag 4, lag 5, and what else? We need the volume. So these are the independent variables, and we need our dependent variable, which is just our direction column. Okay, now we are defining our model, which is SM for the statsmodels API, and then we are using logit and provide our dependent variable and our independent variables. Now we're using that to get a result out of that. So we are fitting the model to those variables. And with that, we can take a look at the summary of this logistic regression to get an overview of the intercept and the coefficients. So as you see, we are getting this table. So these are the coefficients of the independent variables. And as the authors already mentioned, so the lowest p-value is for lag 1, but all in all we have very high p-values here. Yeah, but whatsoever, so we are not discussing statistics here. We want to predict the market. So let's do that. Let's create a variable which we are calling prediction. And now we're using result.predict and provide our features here. So let's print out what we got here. You see we are getting those values here. And in a logistic regression, we have to transform those values. So if one of those values is larger than 0.5, it will be up. And if this is smaller than 0.5, it will be down. To evaluate whether this prediction has been good or bad, I'm using a confusion matrix. So a confusion matrix is just comparing the actual values with the predicted values. So in this function, I'm also doing the transformation of these predictions. So let's create a function here. I'm just calling that confusion matrix. And this function is taking the actual values as an argument and also the predicted values. Okay. So the first step is to transform the predicted values here. So I'm just creating a variable here, which I'm calling predicted transformed values here. So predtrans, and I'm using up if I, as I just said, is larger than 0.5, else down for I in pred, and pred is an argument of this function. And I'm also doing the transformation for the actual values, which I'm calling actuals here. And now I'm using up if I is larger than 0, so y 0 now, because the actual values, so the actual values are the y values. You see that we have 1s and 0s here. So it is up if we have a 1 here, and it is down if we have a 0 here. Okay, just in case you are confused why we are doing 0.5 here and 0 here. Else down for I in act. So act is an argument of this function containing the actual values. And now we are creating the confusion matrix after those transformations. And I'm using the cross-step function for that, so there are many ways to create a confusion matrix in Python. But I think that's a pretty convenient way here. So I'm using the cross-step function, provide a series of the actual values here. So this is just taking this list here as an argument and transforming that to a series. And the second one are the predicted values. So let's get that in the next line here. These are the predicted values. And what else? Right, we have to define row names. And our row names are the actual values. And our column names are the predicted values. So let's just call that predicted. Okay, so finally we are just returning this variable. So I'm just using return confusion matrix. So let's test that out. So we are calling this function confusion matrix and provide the actual values, which are again the y values, and the predicted values are stored in the variable prediction. So this was this variable here. Okay, so let's execute that. And now we're getting this confusion matrix. And just in case you are confused, this matrix is inverted compared to the book version, right? So don't be confused about that. So they are showing the actual values here and the predicted values here. I'm showing that the other way around. But it doesn't matter how you are showing it. The diagonal is always containing the rightly predicted values. So you see, it is predicted down and the actual movement was down. So these are the correct predictions for the down movements, and these are the correct predictions for the up movements. Okay, now let us check how often the model has made the right predictions. Therefore, we are just adding up those two values here and divide that by the sum of all those values here. But we already know how many observations we have by just taking a look at the length of the data frame. So we have 1,250 observations here. So we can just add up 155 plus 504. So let's do that. 155 plus 504 and divide that by the total number. And this value, so this is telling us that this model is making a better prediction than just randomly guessing. So if you are asking any person, what's the stock market tomorrow? He can tell you up or down, and the probability that he's right is 50%, right? So this model is doing a better job than random guessing. And this is, or let's call it like this. This seems to be pretty awesome. But the authors in this book are already criticizing their own model. They are saying, and that's totally right, that the result is misleading because they have trained the model and tested the model on the same set of observations. To avoid an overly optimistic model, the authors have split their dataset into a train and test dataset. The train dataset is only containing dates before 2005, and the test dataset is containing dates in 2005. So in simple words, what they're just trying to do is they're just using the data before 2005 and check what the model is predicting for 2005 and compare that to the actual values in 2005. And that is exactly what we are doing now. So let's create some variables here. First one is the xtrain variable. And now this is just containing, as said, dates before 2005. So we can just use our data frame filter for the date, which is containing a year, which is lower than 2005. And as columns, we are just taking the columns from above. So I'm just copy pasting them. Wait, where are they? Here. So we are adding them here. This is the first one. This is our X train variable. Then we need a Y train variable. And this is just the same syntax here. So again, dates before 2005. But now we are just taking the direction column. Now the test data is just this syntax, but with a equal to 2005. So as said, the test data is just containing 2005 data. And now we are just copy pasting that again. Insert that here. And finally, we have our y-test variable where we are just using this syntax here and take equals to 2005. Well, nice. These are our training and testing variables which we need. Now we have to again define our model. Again, use sm.logit. And now we are providing the training data and so the dependent variable training data and the independent variable training data. So we are just using the model on the training data. So let's execute that. And now we can provide results equals to model.fit. So we are fitting the model to the training data. And we can again make a prediction here. So we're using prediction. And now we are providing the test data, right? And this one we are comparing with the y-test data, okay? Sorry, we're using the predict function. Okay, so we have predicted our values here, and now we are again just calling our confusion matrix and provide the test values. So these are again the actual values, and take our predicted values, which are stored in this variable. So let's see what we got. Now we are seeing another picture here, right? So again, these are the correct predicted values. So let's sum them up and divide that by the total number of observations. So the total number of observations this time is 252. So we can just take 81 plus 38 and divide that. And now you see we are only having a prediction accuracy of 47%. So a random guess would be better than that. So that's quite disappointing, right? But interestingly, what the authors found out in the end is if we are cutting off variables which we don't necessarily need, then we are getting a better prediction. So there were referring to the regression table in the very beginning and just cut off variables. And there were cutting off everything but the leg 1 and leg 2. So let's do that quickly because I think the results were pretty interesting. So if we are doing that and just cutting off this whole stuff here, just execute this cell again and train the model again, fit the model, make a prediction and use the confusion matrix again. And now we are calculating 40 plus 104. And now you see we are getting a accuracy of 57%, which is quite an awesome number, right? So it seems to be, I'm really cautious here, it seems to be that taking only the prior day and the day before the prior day into account, you can do some nice predictions of the direction of the stock market. But yeah, maybe there are other factors, so play a bit around. I hope this is adding value for you, this video. I think it's a very interesting thing. It's a nice combination of finance topics and data science. So if you like this video, please be so kind and show your support. And yeah, I'm looking forward to seeing the upcoming videos. And yeah, have a great day or night, depending where you are. And see you next time. Bye bye.